We now want to discuss a little bit about the chapter 16, right? Electric energy and capacitance. And this first video is going to more or less focus on work and electric potential energy. Okay, what happens to the energy in a system if a charge is in an electric field, right? That's the main question that we want to address here. So what we have, this is the most generic situation to introduce the ideas of the chapter. Suppose that we have a plate, okay, a metal plate that we've deposited some positive charge on, and we also have a negative plate that we've deposited some negative charge on, and these plates will then produce an electric field, E, okay, an electric field E between them. And the main point here is suppose I put some test charge, Q, in the middle between these two plates, embedded into the field, right? What's going to happen? Well, since this is a positive test charge, we know that if I release it from rest, right? So suppose the plates are glued down or held down or clamped down. The plates are fixed, the electric field is fixed, and I place my charge in between the plates and I release it so it's allowed to move. All right, what's going to happen? Well, we know that it is going to accelerate toward the negative plate and it's going to experience a force, QE, right? Remember that F equals QE, okay? So it's going to experience some force, and suppose that we just consider its motion from points A to point B. What's going to happen in that case, right? Well, if you recall the definition of work, right? Work is force times distance. And we already know what the force is. The force is the charge times the electric field, and it's going to move through this displacement delta x from x initial to x final, or from A to B, right? So it's going to do some work, okay? Well, I should say the electric field is going to do some work on the charge, okay? And it's going to do work equal to F times delta x, and F is QE. And of course, delta x is just the final position minus the initial position. And if you recall from last semester, in systems where energy is conserved, the change in potential energy is equal to the negative work that's done on the system. Okay, so in other words, this is going to be losing potential energy. Okay, this system is going to be losing potential energy as the charge, quote unquote, falls toward the negative plate, right? And you can think of it as falling, okay? Just because in this representation the charge is moving to the side doesn't mean it's not, quote unquote, falling in its own reference frame, right? Just as a rock would be falling if you dropped it off of a bridge or a tower or whatever, okay? But the essential point here is that the change in potential energy is equal to the negative of the work, okay? And since the work is equal to QE times the displacement, if our motion is restricted to a straight line, we can replace delta x with d, and we can then say that the magnitude of the work is equal to my charge times the electric field times d, or QED, right? And the change in potential energy is going to be that same magnitude, but with a negative sign, okay? The change in potential energy, well, they're both going to have the same magnitude, the work done and the potential energy, but when I actually take the energy conservation into account and not just look at the magnitude of the work, then the change in potential energy is going to be equal to minus the work, okay? So in other words, what this implies, okay, is that my negative plate here is considered a plate of low potential. Okay, my plate is going to be considered a plate of low potential energy, and my positive plate is going to be a plate of high potential energy. So an analogy that you're probably more comfortable and familiar with would be, consider this negative plate acting as the ground, and imagine this positive plate as acting something at some altitude h, right? And I drop a rock down toward the ground, and I let it fall through some distance h, right? So before it falls, it's going to have potential energy mgh, right? And as it's falling, it's going to lose that potential energy. So the gravitational field is going to be acting on the mass. It's going to lose potential energy, but it's going to be gaining work, right? The work done is going to be positive because the gravitational force is going to be pulling it down, and it's going to be pulling it down with a force mg, and it's going to be moving through some displacement, right, xi to xf. And so as a result, we have a pretty clear analogy here between um, electric potential energy and gravitational potential energy, right? So as if I consider this as a rock, as it's falling, it's going to be losing potential energy while it's gaining kinetic energy in the form of work. And so the analogy still holds that as I lose potential energy, I'm going to gain work. Or another way of writing this would be the negative change in potential energy would be equal to the work. Okay, so that's the essential point here, is that if I can consider my positive plate as a high potential energy and my negative plate as low potential energy, then my analogy with gravity is going to hold ubiquitously. And so what this means is, and I just alluded to this on the last slide, that the work done is equal to QED or QE delta X, and work is equal to the change in kinetic energy. So as the electron, or I shouldn't call it electron, it's a positive test charge, right? If anything, it'd be a proton. But in any case, it's a positive test charge. As this positive test charge is released and accelerates toward the negative plate, it's going to be gaining kinetic energy, so it will experience a change in kinetic energy, and that change is going to be equal then to the work, right? So that's another essential point here with this system. And I've already kind of alluded to this, right? This is what I was essentially saying last time, that as my object falls, quote unquote, falls from A to B, okay, it's going to lose potential energy, but it's going to gain kinetic energy. Now, according to the conservation of energy, okay, if this is a conserved system, and it is, but if it is a conserved system, then the change in kinetic energy plus the change in potential energy should be zero, right? The change should be zero. And so that allows me to then calculate what the change in kinetic energy ought to be. And for my potential energy, if I assume that my initial state A is where I'm going to set my potential energy to be zero, then my final potential energy, or I shouldn't call it my final potential energy, but I'm sorry, I'm going to denote the bottom as zero, right? Because this is going to be potential energy final minus potential energy initial, okay? So this is going to be zero minus my initial potential energy. So I'm going to set my zero at point B, okay? And A is going to be at a high potential, QED, and when I take the difference between those, the final potential energy and the initial potential energy, I'm going to get negative QED, right? And so this is going to then allow me to calculate what the change in kinetic energy is, since the sum here has to equal zero, right? The change in kinetic energy and the change in potential energy has to equal zero. And so I can calculate what the change in kinetic energy is going to be, which is QED, the same as the work. And this is the analogy to a gravitational field. If I denote B as my zero potential, or my 0 point for my potential energy, and I drop my object from point A, then it will have work done on it equal to mgd. It will gain kinetic energy equal to mgd, and it will experience a change in potential energy of minus mgd, right? So you can think of the gravitational analogy here very, very solidly, right? This is a very solid analogy, if that will help you think through charges, quote unquote, falling in electric fields.